Hello, I'm going to comment on my own working model simulation of the punch press. I made some modification over what you saw in my sample screenshots that I emailed out to the class. The basic model is simple. This disc serves as the crank as well as the flywheel for the punch press. The connecting rod, I have this rectangle which is the punch, it's body number 3. On the punch I attached a point number 16, and there's also the workpiece that has 2 points, one on top, one below, point number 22, point number 23, start of punch, end of punch. These points, together with the velocity of, could have been velocity of point 16, but velocity of the punch in the y direction, they serve to define the conditional force that simulates the resistance to punching of the workpiece. These are controls, and I have one for where I can edit the maximum input, the maximum force at the beginning of the punch, calculated as you know, the shear area times shear strength of the material. Here I have the average torque is calculated in Excel, and then here's the moment of inertia of the I hit run so that you can see what the simulation does. The moment of inertia of the flywheel. Okay. You don't have to, but also shown here is this where the workpiece is and the workpiece thickness. I could edit these values. The rectangle resizes itself. It carries the 2 points with it, so that dependency is maintained, as well as stock location. You want to have the stock position towards the end of the punch. I think I mentioned something like in its lower position, lowermost position, the end of the punch to clear the workpiece by a certain amount of stock thickness. Okay. Regarding the simulation, if correctly calculated the average torque, then this zigzagging line in green, this is the velocity of the flywheel. It's going to remain zigzagging, yes, but will remain horizontal. Otherwise, a too small average torque, zigzagging will go down. If too big average torque that you apply to the motor, zigzagging will move up. As for the moment of inertia, if correctly calculated using the minimum and maximum minimum values of the velocity of the crank and an average velocity, which by the way I have it also defined as a control. You don't start from zero, the simulation, for added realism. So with the maximum minimum values and the average values, you can calculate a coefficient of speed fluctuation, and that should be close to, again using the simulation values, should be the one that you used when determine the required maximum inertia of the flywheel. Meters, I have the punch force, the crank torque, although I edited the limits to where I can see magnified how the torque varies right before or around the period of the cycle where punching occurs, and then there's the velocity. Again, this is with respect to time, and that is the horizontal axis is time, and you can learn how to move this away. Okay, looks like you can move it away. So from 0 to 8 seconds, multiple punching occur. So as you can see, zigzagging is steady, it doesn't go up. Input values are consistent. Let me explain how this conditional force has been defined. So I go and open force, and you can see here there's 0 on the horizontal axis. As you drag and apply the force, by default we'll have, depending on how you play with the mouse, some x and y values and constant. I have 0 horizontal component. The y component is an equation, and it uses the velocity of body 3 dot v dot y, that's velocity, and then it uses the position of point 16, which is this one, and the positions, p stands for position in the y direction, p in the y direction, position in the y direction of points 22 and 23. Okay, as well as the input 33. This is the maximum force, which it's read from this control. Okay, so the way it works is if velocity in the y direction of the punch, body 3, it's negative, that is, the punch moves down, and if point 16, it's between point 22 and 23, that is, y of point 16 is less than point 22, but y of point 16 is greater than y of point 23, then I have this equation, which is that linear variation of the force, and I'm not going through the details otherwise. So if the punch moves up, it's 0. If the point 16 is not between 22 and 23, it's also 0. Okay. In addition, I'm asking you to also have a couple of measures. So I want you to, measure the displacement in the y direction of the punch, and also not as function of time, but rather as function of, let me take it from here. So as function of the position of the crank. So crank is body 1, position dot rotation. Here you see a mod. It's the modulo of the crank angle, modulo 360. Angle is in degrees. So this graphs is going to be limited to 0 to 360, and simulation continues. Crank rotates past 360, but with this definition of the y-axis, I'm still showing activity occurring over the graph and not outside of the graph that is to the right. So just a detail. Anyway, in our case, all we want is just the position. So this will be theta only, and what else? I also want to. So I have the auto should go to off and 360. And we also need to see what the limits for a better than the default ink to paper ratio, which is called. So I need to wait for a full cycle, and then we'll do velocity and acceleration in a straightforward way by just copying this meter graph. Okay, so I'm waiting for just one cycle of the simulation, for the position graph to be populated. And this is it. So I've got one cycle. I go here. You may hear some background noise. Sorry for this. So I have negative 0.8, the minimum value, to negative 0.4, the maximum value, and then the velocity. Okay, let's do this appearance and show name. I could make this into a punch. Save often. I haven't done my 2004 version of Working Model. It's a bit more stable. But yeah, save often, and let's see if this does. I can fix it by doing so. So I have punch displacement, window, appearance, and this should be S. Don't know what happened. And then, so I have punch displacement. I click on this meter, say edit, copy, and then paste, and I can change this quickly into the velocity of the punch. I just changed what was P dot Y. I'll change it into so this will be ds over dt. One thing, so it's punch displacement. That punch displacement is actually measured to the center of gravity, that is the geometric center of this rectangle. So it will the displacement graph will be offset by what? By the height of the rectangle, and I could add that as an offset, or I could use, so actually for maximum realism, or to match exactly the yes, should rather use, okay, so let's see, 0.28 and measure position, and I'm saying 0.28, so it's 0.28 position Y. Okay, so I made a change if you notice. So okay, so instead of adding a bias, I went to this point. I delete this point. C now is going to be the punch displacement. Velocity and acceleration doesn't matter. The points move with the body, so they will be the same. So I'm continuing. So body 3, velocity in the y direction, and of course the acceleration, the velocity will have a different limit, and we need to wait for a full simulation to happen. And why is that? Okay, so two things I need to do. I need to correct the limits on the punch displacement. Again, is not the center of mass of the rectangle, or at the point C, which was S in the spreadsheet in Excel. And here too, to add to increase the ink to paper ratio, I'm just going to edit the limits, so the maximum will be 2 meters per second, going from negative 2 meters per second to positive 2 meters per second. Okay, so this first we said -2 to 2. As for this graph, I know the bias, it's 0.15. I looked at the graph. So what the graph did, it went up by 0.15. So this can go to 7, and this can go to 3. Is a 3 a good value? Looks like. Okay. So now we have, and of course this has to be updated, punch velocity. Save often so that you don't lose your work. And I could do again, copy and paste to edit this. Edit, copy, paste. This is paste, and this will be the acceleration. How do I get acceleration? Say, or replace V with A, and this is, I could say dd second derivative. And of course you would need to edit limits, but this is the basics. And as I wrote in my emails and told you verbally, I'm expecting the working model to be to validate your spreadsheet work, and the position, velocity, and acceleration of the punch would be one way. Another parameter that you could also plot, or you should also plot, is it's the transmission angle. You saw me what I did. I took the connecting rod out of the assembly. I typed for the angle 0, and this is a confirmation that when I generated the link, what I actually did was to I drew this way. The better way of doing it is to draw it like so, and then you rotate it. So let me make the change. I'm looking at the height is 0.5, and I'm going to just change this. So I delete this. Window, geometry, and I'm just going to swap 0.5, 0.02, and again 0.02. Okay, and it should be, look at the snap at the ends, the middle end point, and I'm using this tool, and then this goes back into the assembly, split again, and the angle, if I make the angle 0 degrees, it goes to horizontal. So only now plotting a meter or measure of the position of rotational graph. Now, so what I did, I clicked on the connecting rod, measure, position, rotational graph, and if I want to plot it as function of the crank angle, like these other three, actually all but this graph, which is preferred. So I'm going to change time to body 1 position. Of course, this is theta now, the input angle, and then the range of, I changed it to 180, and then although I know it goes around 90, some amount, and then 360. These are the limits for theta, and this will be pressure angle. Okay, window appearance and pressure. Rather transmission, I'm sorry. Transmission angle. So transmission angle, it's the correct name of the graph, and I could say, I think we use phi as a name for the transmission angle, and just one more simulation cycle. The acceleration hasn't been fully edited, but the transmission angle has that symmetric like bell curve appearance, and you can go further and edit the limits, some occurrences on the acceleration. Okay, and we'll be done in just a little bit. Appreciate your patience watching this 22-minute tutorial. So yeah, we can change this to 150 maybe. 150. And as for acceleration, come on, window appearance, or rather Windows properties, and it goes from, what would be a good guess, maybe -10 to 10, -10 to 10. Something happened, maybe more than plus 50. Okay, this is natural. It's because of the impulsive force. It's not going to show in Excel, but it looks like 20. It's an even better value. So other than the spike, this graph, this other one, so the four graphs that we added to the simulation should be the same as in Excel. And really I could go here from 60 to 120. This transmission angle. Okay, so this being said, we will stop the recording.